16-bit real mode memory addressing. I know we're on video 6. I'm probably not going to make individual instruction videos. Yeah, so if you're looking for individual instruction videos, look elsewhere. I will not be making them because there's already so much content and so many videos on them, and they're all really great. So please go use them. I just want us to have a bit more of a focus on actual using assembly in a dev environment. Anyways, memory addressing. Let's look at C pointers. If you're using C, you have int and then star and C pointer, asterisk, whatever. C pointer is the memory address, and then asterisk C pointer is the contents of that address. So everybody should have that down. In assembly notation, it's a little different, but it's actually pretty easy. If we say mov AX 0x5f6d, that is moving an immediate value of 5f6d into AX. That is not memory addressing. But if we want to do memory addressing, we have to put square brackets around it and then put the size of the operand and the register that we're going to be moving it into. So that would turn into mov AX, comma, word, and then in square brackets 5f6d. And that is actually moving the contents of memory address 0x5f6d into the register AX. Nice. And operands must be the same size when accessing memory, which is why you put word in front of the square brackets. All right, labels store the offset of the first byte in the next instruction, so labels can be used to address memory. So you could say my char db stands for defined byte, and then the char c, and then you could move my char into AL, or the contents that are at my char, which is the lower C ASCII character. And you can also do register indirect addressing. We can use registers as pointers. That's actually really cool. That's very fun. In 16-bit, you can only use BX, SI, DI, BP, and SP for pointers. So let's say we could mov 5F6D into BX. Well, now we can turn that immediate that we just used into an actual memory address inside BX when we do mov AX word BX inside of square brackets. Yeah. And then, that would point us to 5F6D. All right, displacement makes accessing stacks and arrays in memory more efficient. Very nice. Instead of manipulating a pointer with another instruction, it can be encoded in one instruction. And what I mean by this is, you say add BP4, then mov X word BP. I mean, you can say that, or you can do mov AX word BP plus 4 in the square brackets. And this isn't that abstracted because that first one is 2 instructions, add BP4, mov AX word BP, 2 different instructions. When you say mov AX word, memory addressing BP plus 4, that's actually one instruction. The processor has ways to, make that one instruction. So you're actually saving space whenever you do this. So yeah, pretty cool. And then there's other things like BX plus SI, BX plus DI plus 2. You can probably guess what that's doing, but so I've gone ahead and removed the stuff from the last video, so we're just left with start label and jump $. I guess first I want to do is that example I had in one of the slides, which is the my char. And then you can define byte C, my char dbc, in single quotes. And I don't know, I could do something like mov AX, my char. Now this isn't moving C into AX, this is moving the memory address of my char into AX. So I could do something like push AX and then call hprint. And go ahead and assemble that. And you can see it prints out 7C09, which is the memory address that the char C in ASCII is stored. And so what we could do is we could mob al bytes square bracket my char, so we can actually memory address it. Print it out on screen using interrupt 0x10. So we can mob AH 0x0E for the tell type output again, and then int 0x10. And then bam, we get the char C printed out on screen. So we know how to loop via the last video, and now we know how to memory address. So now we can print a string actually of characters. So I'm going to rename my char my string. And let's do hello world. Let's do hello world with an exclamation point, comma 0. So I want to start off by mobbing into SI my string, my string. So this will get the memory address where my string starts. Now we're going to loop. I want to compare SI to 0 for that null terminator that we added. Again, this is comma 0. Whenever you define your string, that's the null terminator. I actually want to compare the byte that is at SI, so I will memory address SI with the square brackets. And if it's equal to 0, that's the end of the string, so we're going to go ahead and end going through the string. So I'll just name this string loop above that compare, and then another label for end string loop down there at the end. And we'll jump to that end string loop after we are, done with the string. And to get to the characters in the string, I'm going to increment SI and then jump back up to string loop. And though when we increment SI, it's going to be moving through memory. It's going to be moving across that HELLO, etc. And so we want to actually print it on screen. So after that conditional jump equal, we can mob AL, the byte that is in SI right now, and then mob AH, comma 0x0E, interrupt 0x10, int 0x10. And this will print hello world. Nice. You can actually do something a little better with this. You can put that mov AH up before the loop starts, because it's going to stay the same the entire time. So there's no need to have that instruction inside of the loop. And I can save that and assemble it again, and it'll still work. So yeah, this is just example beginner stuff. There's actually like specific instructions to print, to help print strings, I should say. But we won't look into that until we are actually getting into other things. So yeah, I will see y'all in the next video.